Hello, today's lesson is on section 2.1, representing relations and functions. So we want to learn what is a function and how do you graph functions. So before we move into the section here, I want to look at a couple vocabulary terms that are in your textbook. So we'll pull the textbook up right here. The first one is a relation. A relation is a mapping or pairing of input values with output values. The set of the input values is the domain and the output values is the range. So typically in an XY table, as shown here, the X values are the domain and the Y value is the range. So there's four ways that we can represent a relation. We can represent it as an ordered pair, a table, a graph with the coordinates plotted, or a mapping diagram. You've seen these three before, but you may not have seen the mapping diagram. So the mapping diagram shows the inputs and the outputs. The arrows indicate the output that goes with the corresponding input. So let's just go through an example here. And let's say we are given the relation -2, 4, 3, 5, and 5, 8. So can you identify what the domain and range is? So typically it's shown like this with a D, a colon, and you just list the domain. So the domain again are the inputs or the X values. So that would be -2, 3, and 5. The range would be 4, 5, and 8. That's how you'd show that. Okay. Next thing we want to look at is the term function. Okay, and again, in your textbook on the top of page 73, I can pull it up right here. It says a function is a relationship for which each input has exactly one output. Okay, that's a key definition there. So each input has exactly one output. So for example, let's look at this number 2 here then. Let's just say I have a relation shown in a table, and we have there's my domain, and there's my range. So does each input have exactly one output? Each input, there's 4 separate inputs, so each input has exactly one output. So this would be a function. Let's look at another one. Okay, so looking at this chart, this table, each input is mapped to an output. However, what do you notice here about the input of 1? It's listed twice, it has 2 separate outputs. So because of that, this is not a function. Okay, finally one last one there. Okay, so at first glance you may say this is not a function because -1 is listed twice as an input. However, it has the same output. So even though this is listed twice, it's the same pairing. So each input has one unique output. So this would be a function. Okay. So now the next question is graphically, how do we determine whether a graph is a graph of a function or not a function? So we're looking at graphs of functions. Okay. So let's just do a simple graph that you've seen before. A parabola y equals, we'll say that's y equals x squared. Well, it may not be exactly y equals x squared, but is that a function? For each input, each value we put in for x, and we square it, we get one unique output. Okay, so this is a function. So if I look at any x value on the x-axis, I can map it, or I can come up and across to one unique y value for each x value. So this is a function. Now, that is opposed to a graph that may look like this. Or something like this. Kind of like a sideways parabola. This would be not a function, because for an x value, let's say we look at -2 here. -2 could be mapped to two separate y values. So this is not a function. So how do we determine whether a graph is a function? We do what's called the vertical line test. So if I'm given the graph, if I can draw a vertical line and it goes through the graph in more than one location, that would indicate that the graph is not a function. So in this case, if I drew a vertical line, say here, crosses the graph in two spots, that's not a function. However, for this one, no matter where I drew a vertical line, it would only go through the graph one time. So this one would be a function. So that's called a vertical line test. Okay? All right. Next thing, graphing a function or relation. We've all done some graphing before. In this section, it's pretty straightforward. So let's say I want to graph y equals -2x plus 3. Now you may know some shortcuts on graphing that, but in this section they want you to make a table. So step one is to make a table. And we're going to run our table of domain values from -2 to 2. So all we're going to do is substitute that in for x. -2 times -2 is 4, plus 3 is 7. -1 is going to be 2 plus 3 is 5. This is going to give me 3. This will give me -2 plus 3 is 1. And then -4 plus 3 is -1. Okay? We've done this before. We graph our coordinates, plot our points. -2 is 7. -1 is 5. 0 is 3, 1 is 1, and 2 is -1. Okay, and then we connect our points here. I should use a ruler, straight edge, but there's my graph. Okay. So, anytime I have a linear function, that would be or linear equation, that would be a function. Unless, of course, it's the equation of a vertical line. That would not be a function. Okay. In this section, they also talk about function notation. So function notation. So we're used to this. Y equals mx plus b. We've seen that before. This is slope-intercept form of a line. The m is the slope, the b is the y-intercept. This would be function notation. the way you'd read that is you'd say f of x equals mx plus b. All it is another way to write y equals mx plus b. A lot of time, the parentheses here does not mean multiplication. It's just the function. It's naming the function. And the f could be any letter. It could be g of x equals something. Okay. Often that letter is in a real world meaning. Okay. P of x might be profit for a company, something like that. Okay, so let's look at an example here. Let's say f of x equals 2x plus 3. Evaluate f of 5. Okay, what that means is all we do is we take 5 and we plug it in the equation for x. 2 times 5 plus 3 would be 10 plus 3 is 13. Okay, so the value inside the parentheses is what we substitute in the equation. Okay. And finally, the other thing in this section is linear versus nonlinear. Okay. So anything that can be written in the form of that, y equals mx plus b, is linear. Okay. Anything that is doing something to the x, like squaring, things like that, would be nonlinear. Okay, so let's see if so for example, let's say I have f of x equals 5 minus 3x. Linear or nonlinear? Well, can I write it in the form of mx plus b? Sure I could. I could just rearrange these. This would be linear. Okay. What if I had something like this? X squared minus 5x plus 4. Well, because I have a squared term, that would mean that it would be nonlinear. I can't write it in slope-intercept form. Or what if I had this? Linear or nonlinear? Now, if I just looked at what was inside the parentheses, I would say that's linear. However, the entire function, when I distribute, would actually be 2x squared minus 3x, which is nonlinear because of the squared. Okay. What about this one, last one? Okay. This f of x equals absolute value of x minus 3, or minus 3 minus 2. Okay, because of the absolute value, we cannot put this in slope-intercept form. It's nonlinear. Okay. Even if I had a cube term or a fourth power term, that would automatically make it nonlinear. Okay, so this concludes section 2.1 on function notation, representing relations and functions.